Today we're going to solve the Runge-Kutta method example given in Wikipedia. The example in Wikipedia is a pretty simple example, and the advantage here is that we can compare to the analytical solution. We're not going to go a lot into the theory of it. You probably, if you need to write the code, you probably already know something about the theory. But in essence, you have a differential equation. We have here an example of usually a ordinary differential equation. You have here the derivative term, and then you have here a function that corresponds to the derivative here. So this is a very broad way of talking about that. There's a lot more in differential equations, but let's put it like that just for simplicity. You have to solve this differential equation given some initial condition or some initial conditions. Depends. You can have partial differential equations. You can have all sorts of things where you have different boundary conditions and initial conditions. But in this case, it's a pretty straightforward ordinary differential equation where you have just one initial condition. The equation that we're going to solve is this equation here. So you see here dy dt equals sine t squared times y. So you have one first derivative here, and here you have a function in t and y. So we know that the derivative of this equals this function, and we want to solve that to have an analytical expression of y as a function of t. You can solve that analytically, so you can get the analytical solution, but the purpose of this video is to solve this numerically using the Runge-Kutta method. So when you don't have an analytical solution, you can do a numerical solution approximating the solution. So to implement the Runge-Kutta the fourth order Runge-Kutta, all you have to do is follow this simple algorithm here. So you have an approximation in n iterations here. So you have y in n plus 1 equals y in n plus 1 over 6 h, which is the step term or step size, plus here in parentheses the Runge-Kutta coefficients. So the Runge-Kutta coefficients are defined as k1, k2, k3, and k4. This f here, you can see here there's an f here in dy dt, and this f appears here, is the form of the function of your differential equation, talking in very general terms here. So for example, in this equation here, you can see here on the left side, let me just increase a little bit the size here. In this equation here, you can see that y here is dy dx, this y prime here, and the function here, the f function here, is sine t squared times y. So we're going to solve this in C. I'm just going to open a terminal here, because C is pretty straightforward to solve, and it's better if you're learning to use statically typed languages like C or Fortran or C++. So I'm just going to go into my folder where I'm saving these codes. I'm going to create here, I'm going to use vim Runge-Kutta 4.c. So now we're going to write our code here. As usual, for a C code, you have to include some libraries. Let's include the standard input output h, and let's include here for our mathematical functions math.h library. Okay. Now we write our main function. Let's just put the return 0 here so we don't forget to put it later. So this is the basic that you need to write your C code. Much of the algorithm that I'm using here, you can approximate to Fortran or Python or whatever, or C++ is almost the same thing, and you can approximate this code or translate this code to other languages. So what we're going to need for this function, let's take a look here again at Wikipedia. We're going to need a maximum number of n here, or iterations, and we're going to need the step size. So let's define that as constant or as parameters in our function. We can define that within the code, but let's just define it outside. So let's define age. Let's put 0.5 and let's define in max. Let's put 100. You'll see later that we need to change these steps here. Now we can define the variables that we need for our function. We're going to need two arrays here, or two for the time and the y predictions. Let's call this y. The size of this array would be n max. These arrays would be n max, and the t here would be n max. We need this because, as you can see here on the algorithm, this time here and the y, they're going to be iterated over n. So we're going to need several. We're going to need an array to store these values. Okay. So now, what we need to do is to write this algorithm here, so we can solve it by iteration. So let's create a for loop here. I'm going to put the rest of the variables as we need it. We'll need them. We're needing for n equals 0. So I'm creating the iteration here, n less than n max, which is the maximum value that we declared there, n plus plus, so this creates the iteration. I'm going to setting this as a loop. We can now define, obviously we need to define n here as an integer type. Now we need to create our functions inside here. Okay, so let's first write these two functions here, the functions that are going to be iterated. Let me just split this here so it makes it easier for us to work on that. Okay, so just write this function here. We're going to have a function y n plus 1, the plus 1 iteration here, equals y n plus 1.0 over 6. I'm going to put the 0.0 here because this could give you a lot of heartache in C because of the conflict between types of variables. Times h, which is the time step that we're using for increasing t in this case, times k1 plus 2 times k2 plus 2 times 2 times k3 plus k4. So the Runge-Kutta coefficients here. Let's not forget the semicolon here. Same thing for t. I'm going to declare here t n plus 1 equals t n at the first initial condition plus h. Okay, I'm going to declare here the initial conditions. The initial conditions is that t at 0 equals 0. If you look at this function here that is given in Wikipedia, you're going to see that, difficult to see here, but the initial condition for y here is around 2. So you cannot start with 0 because that could give problems with solution. So the initial condition for y is that y 0 equals 2. So those here are the initial conditions, and the solution of the differential equation obviously depends on the initial conditions. Okay, So now we need to input the coefficients. Let's first declare these coefficients here. Double K1, K2, K3, K4. I'm not gonna use functions here. I could declare this equation here and then use it as a function, but I think it's simpler if you want to translate that into other codes, or if you want to implement it yourself, to not use the functions. So let's just declare this Runge-Kutta coefficients here, and let's just write their equations. K1 equals f of t n yn. So what is f, t, n, yn? Like I told you before, it is this function here. So f is sine of t n. Problem here is that we have a square, so there's other ways of doing that, but let's just use the power function, which is simply the power, and you can use the order here that you use. So this is equal to sine t squared times the second coefficient here, which is y of n. Okay. Now we write the second, third, and fourth for Runge-Kutta coefficient. Now the f here is of tn plus h over 2 and yn plus h times k1 over 2. So this would be then how the sign here is of tn plus h over 2.0, close this here, power of 2 times, now we have more than one thing here, yn plus k1, sorry, plus h times k1 divided by 2.0. Okay, let's close our parentheses here. There's one many here. Same thing for k3, or a similar thing for kt. All sine of this whole thing here, t of n plus h over 2.0, second order, times y of n times h, sorry, plus h k2 over 2.0. Close here, k4. Now it's simply phi O of sine of t n plus h power of 2 times hy of n plus h times k3. Okay, so I think it's everything is correct here. So we're gonna loop over this here. The order in which you put the coefficients or the equations here that you're solving matters, because if you put them above here, you're gonna have one last pass, and that could be a problem. Okay, now we want to see the results, so let's put this here. Let's get a print function here. Print float. Let's put a tab here. Gonna be clear in a minute why I'm putting a tab here. Float, and then we call these variables here, t of n, y of n. Okay. All right, so let's test the code, see if there's something missing here. Okay. I'm gonna open a second terminal window here. I'm using Linux. If you're using Windows, please check the video where I teach you how to install mingw and write C code in Windows. So let's write a new tab here, and we're gonna compile it in using the GNU C compiler. The input file is rk4.c. The output here, let's call it rk4. You're going to see that there's an undefined reference to mathematical functions, and then we need to call here a flag here, a statement ln, so it can understand, the program can understand the mathematical functions. Okay, so it compiled. Okay, let's just run it. rk4. Okay, so there's some things that we need to fix here. The first thing is that let's put a line here after each iteration. Save it, run it again, clear this here, run it again. Okay, now you see that the function here that it's solved in Wikipedia, it goes for time around 5. We're going to time around 50, and this is causing the values to explode into very high values around infinity or something like that. So we need to either increase the time steps here or decrease the number of the n max. So let's decrease the n max and see what happens. Okay, let's run it again. Okay, now we have a solution at up to around 5. I think you see here that they're using 0.5, but I found that that is pretty coarse for our the purposes that are going here. So let's refine this mesh a little bit, this time step a little bit. I'm going to put 0.1 here, and let's see if this n max is sufficient. It's not going to be sufficient to reach 5, but let me show you how that works. Okay, so we're going to 0.9. We can increase now the number of time steps. Let's put 100 now and see how far we go. You can play with this time step and number of iterations, so you can find an ideal combination for the precision. I'm not going to go into the precision and stability and convergence procedure, but this is important. This is just a simple example. So you see here that we're still going to 9. So let's try to put 0.2 here or test. Let's try to go back to what we had before. Let's put 0.5 here and 10 here. Okay, so we're going up to 4.5. I'm going to put one more time step to see this improves things. Actually, put 50 here. Let's put 0.1 here. Okay, so now we're going up to 4.9, which is around what is being simulated here. Okay, 4.9. Now you need to test to see this is the solution of this is the numerical solution of the procedure. And now we can test it to see how close it is to the analytical solution. Keep in mind that, as I mentioned before, you're not always going to have an analytical solution to test, but to test your numerical solution. But because this is a simple example, we can do that. Okay, so I'm going to copy this here. Instead of writing a code for plotting right now, I'm just going to put it in a worksheet here. Okay, let's just import this. I'm gonna put those two here. Delete this here. Include a row here. This is T, and this is YRK4. I'm gonna put the chart here. You can see here that the numerical solution pretty much follows what you saw in Wikipedia, right? Pretty much follows the procedure. You can test this with the Y analytical solution. Yeah, this equation should be pretty straightforward to solve. I'm not going to solve it here. I'm just going to get the analytical solution of this equation from Wolfram alpha. This is the analytical solution. Okay, so let's write this analytical solution here. This here, the differential equation solution, which is, you have a C1 here. C1, I think in this case should be 2. The same thing here. So y over t here, the analytical solution, is equal to d2 times exponential of 0.5 times t, which is this here, minus sine of t times the cosine of t. Okay. Okay. So this is the analytical solution. You see that the precision is very high in this case. So the values are very close. Maximize this here, and I'm going to do another plot. So the values are so close that you cannot see the second curve. But if I delete one curve here, the other curve is below it. Okay, so we were able to solve the example, the Runge-Kutta example from Wikipedia, this equation here, y dy dt sine t squared over y, using the classic Runge-Kutta order method. So you just need to, if we're gonna write a function for the Runge-Kutta, the function for the Runge-Kutta is just this here. Okay, so you can implement this as an external function and call it every time you need it. If you need to write this in Fortran or in Python or in other languages, it should be pretty simple. It's just a matter of defining your arrays here at the beginning, and then implementing a loop here which iterates over n time steps, and then you can refine the better the maximum number of steps and the time steps here. So this is pretty straightforward.